In this presentation, we will talk about how we approach the problem of building an automated bubble machine, how we use the engineering design cycle, and how we use the specific steps as a key to generating success through our teamwork, what changes made along the way to our project, and for what purposes those changes were made, and we'll also try to give you a brief summary of how everything came together to ultimately work out in the end. During our first team meeting, we defined the basic problem that we would be working on together, of which the basic requirements were to build a machine that could automatically produce bubbles that would detach from the machine and float on their own. Afterwards, we assigned specific duties to maximize team efficiency and assembled the team as laid out in our team contract. We then identified the main constraints and criteria for the competition, of which our main concerns were the fact that we could use no more than 6 volts of battery power, we were limited to a $40 budget, and we must submit our own bubble solution with our recipe submitted to the judges. Afterwards, we began brainstorming solutions to the problem and started working on our basic designs. While researching successful bubble solutions online, we found that the addition of glycerin to a solution made the bubbles much more durable without having any negative effects on the amount of bubbles that were able to be produced. Using this information, we began testing several solutions with varying amounts of water, dish soap, and glycerin in them to determine which would provide the best bubbles. After several trials of solutions with differing amounts of these ingredients, we determined that the best solution contained 4 parts water for every 2 parts dish soap and 1 part glycerin. Not only did this provide a great amount of bubbles, the bubbles were also much more durable and lasted much longer when coming in contact with other objects. While coming up with our initial design, we decided on a pinwheel-like motion of the bubble wands rotating through a container of solution at the bottom. The next step was deciding whether the pinwheel be powered by the wind from the fan or if it would be powered by a small voltage motor. After discussion, we decided that the motor would be more reliable and would still fit well within our budget. After a trip to Radio Shack, we soldered together a 1.5 to 3 volt motor to a potentiometer so that we could control the frequency of the motor and thus change the size and shape of the bubbles. We soldered that to a switch and then to the battery supply, and we used 2 AA batteries to power the motor. After acquiring some blue insulation foam and a fan from members of the group and purchasing a tray for the solution to sit in, we began setting up the basic layout of the machine. Our initial plan was to have the fan on one end of the foam blowing perpendicular to the rotation of the pinwheel. However, after some thought, we thought that having the fan blow parallel to the motion of the pinwheel would create more bubbles and also make it easier for the bubble wands to get fully coated in solution. The next problem we tackled was attaching the bubble wands to the rotating motor. To test this, we first tried using half of a stress relieving ball, but the motor kept drilling a larger and larger hole until it would no longer spin. Next, we tried using a cylinder cut out of the insulation foam attached to the motor, but it caused too much friction and we began smelling smoke, and again the hole kept getting drilled larger and larger until it would no longer spin. After superglue and hot glue both failed to bond to the insulation foam, we began searching for alternative solutions. One member of the group came up with using air-dry clay to mold the wands together and then using hot glue to attach these to the motor. We allowed the clay to dry for 2 days and then used hot glue to secure it to the motor. However, again, the hot glue was unable to stay attached when the motor began rotating. We finally discovered that duct tape worked well in keeping the wands attached to the revolving motor, and this is what we ultimately used in the end. With the wands now attached by duct tape, we began testing the machine with the fan blowing parallel to the pinwheel as we had planned. However, after several unsuccessful attempts, we decided to reorient the wands and move the fans that would blow perpendicular to the wands. Almost immediately, the machine began producing bubbles, so we began searching for ways that we could improve the performance of the machine. We determined that if we could channel the air and make it more focused, more bubbles would be able to be produced. So we made a wind tunnel out of a plastic bag taped onto the fan with a hole cut out at the end. The wind tunnel worked as we had hoped, and it made the air more concentrated and was thus able to produce more bubbles from the machine. Despite having to make some modifications to the duct tape while it fed, our design worked well. The fan blowing perpendicular to the pinwheel gave the air more time to produce a steadier stream of bubbles, and our solution did produce a high frequency of bubbles. To summarize, we analyzed all potential solutions, whether it be for our bubble solution or for the design itself, and then chose the best solution that worked best according to the engineering design cycle. We began brainstorming possible improvements like reorienting the bubble wands and then tested these to validate the improvements in performance. We then recorded these results. Collectively, through our group efforts, we were able to make an operating bubble machine within our budget and allotted time frame. These were the references used during our project and during our presentation.